Welcome to lecture 42. In our previous lecture, we started our discussion on simplex method for solution of linear programming problem. So, we will continue our discussion on simplex methods, and in this lecture, we will take an example of linear programming problem and solve it using simplex method. So, to solve a linear programming problem using simplex method, let us first look at the steps that are necessary, and we are talking about a maximization problem. First, we express the problem in standard form, then you start with an initial basic feasible solution. So, to start with an initial basic feasible solution, your set of equations have to be converted to canonical form. Now, we use inner product rule to find the relative profit coefficients of all non-basic variables. For basic variables, these values are 0. If all the relative profit coefficients are non-positive, then the current basic feasible solution is optimal. Otherwise, select the non-basic variable with most positive relative profit coefficient to enter as basic variable. Apply minimum ratio rule to determine the basic variable that will become non-basic variable. Check if the current basic feasible solution is optimal by calculating the relative profit coefficients for all non-basic variables and repeat the cycle until optimality conditions are reached. So, basically you first express the linear programming problem in its standard form, and then you start with an initial basic feasible solution. We have to find out the relative profit coefficients using inner product rule for all non-basic variables. The non-basic variable with most positive relative profit coefficient will enter as basic variable, and we apply minimum ratio rule to determine which basic variable will be converted to non-basic variable. And after this, we will check if the current basic feasible solution is optimal by calculating the relative profit coefficients for all non-basic variables. If the relative profit coefficients for all non-basic variables are less or equal to 0, then you have optimal solution. Otherwise, we will repeat the cycle until optimality conditions are reached. So, let us take this example. We are taking a simple example of two variables with two inequality constants. So, maximize z equal to 6x1 plus 8x2 subject to 5x1 plus 10x2 less or equal to 60, x1 plus x2 less or equal to 10, and there are non-negativity restrictions on decision variables x1 and x2. Clearly, the problem is not in its standard form, so you have to express it in the standard form. So, you have to express the linear programming problem in standard form by introducing two slack variables S1 and S2, because we have two less or equal to type inequality constants. So, we have to add two slack variables S1 and S2 which are greater or equal to 0 to make them equal to right hand side. So, we add S1 and S2, so and rewrite the constant as 5x1 plus 10x2 plus S1 equal to 60, x1 plus x2 plus S2 equal to 10. Note that these slack variables S1 and S2 are also restricted to be non-negative. That means, S1 and S2 will also be greater or equal to 0, similar to x1 and x2. Also, the slack variables S1 and S2 do not participate in the objective function. So, their cost coefficients are 0. You also note from the set of constant equations that you have a canonical form here. So, S1 and S2 can be chosen as basic variables, and then x1 and x2 will be non-basic variables which can be set to equal to 0. So, this is my linear programming problem in its standard form, which clearly shows the canonical form where S1 and S2 are basic variables. Non-basic variables are x1 and x2. Now, to solve the linear programming problem using simplex method, we compute the steps in a tabular form, and this is the initial table known as W1. So, look at here, this CB means cost coefficients for the basic variables, and here are the basic variables or bases. So, this is Cj, the cost coefficients for all x1, s2, s1 and s2. This part are basically the coefficients of these constants. So, note 5, 10, 1 and 0 for S2. So, 5, 10, 1 and 0. Similarly, if you look at the next constraint, the coefficients are 1, 1, 0 for S1 and 1 for S2. This column is for the solution or the right hand side vector. So, 60 and 10. This column is for the ratio BI bar EIS bar. Here in this row you write Cj bar, which is the reduced or relative profit coefficients. So, now let us try to understand how the computations will be performed. So, we learn from here that we can start with the initial basic feasible solution S1 and S2. And then we write the coefficients of these constants. These two rows correspond to coefficients of these constants. Here I have put the right hand side vectors. Now, let us find out the relative profit coefficients. Note that here the cost coefficients for all x1, x2, s1, s2 are given. For x1 it is 6, for x2 it is 8 and 0 for s1, 0 for s2. So, now I can make use of the inner product rule to find out the Cj bar, the relative profit coefficients. For the initial basic feasible solution, I have S1 and S2 as basis, and for S1 and S2 the Cj terms are 0. So, the cost coefficient for the basis S1 and S2 are both 0. So, Cj bar for x1 is basically will be Cj for x1, which is 6 minus 0, because Cb is 0 for S1, S2 both. So, basically the Cj bar or the relative profit coefficients for both x1 and x2 will be same as Cj for x1 and x2, which is 6 and 8. Now, we have found out the Cj bar. Note that for the basic variables, the Cj bar are 0. So, you know the right hand side constant 60 and 10. So, S1 equal to 60, S1 equal to 60, S2 equal to 10. And x1 equal to 0, x2 equal to 0. This is the solution corresponding to this table. So, this becomes z becomes 0, because x1 equal to 0, x2 equal to 0. So, irrespective of the value of S1 equal to 60 and S2 equal to 10, since their coefficients are 0, we have z equal to 0. Now, let us see how do we calculate the ratio Bi bar divided by Ais bar. So, Bi bar 60 divided by 10. Why 10? Because we have to now choose focus on this column. We are focusing on this column because after we have found out the reduced or the relative profit coefficients, we see that relative profit coefficients for x 2 is most positive. So, most positive C j bar enters basis. So, x 2 enters basis. So, I, which stands for x 2 here, so C j bar tells me to find out which non-basic variable will enter the basis, and we find that from the most positive value of C j bar. So, this B I bar by A I S bar have to be found out corresponding to this column. So, I B I bar divided by A I S bar are calculated as 60 by 10 is 66 and 10 by 1 as 10. The minimum ratio rule tells me that the minimum of B I bar divided by A I S bar will leave the basis. So, S 1 leaves the basis. So, S 1 leaves the basis and x 2 enters the basis. So, the pivot variable is 10. So, now what we will do is we perform elementary row operations on the pivot row, that is row 1, and we will make the coefficient of x 2 here as 1 and everywhere else 0 in this column. So, to do that, first what we do is we multiply the first row by 1 by 10. So, this becomes half, this becomes 1, that is what we want, this becomes 1 by 10, so on and so forth. Then what we do is we take second row and subtract from it first row multiplied by 110, then this becomes 0. So, if you do this, you will get this table. So, you go to table 2, note x 2 is coefficient of x 2 is 1 here in the first row, in the second row this is 0. So, in the previous tableau we have seen x 2 enters basis and S 1 leaves basis. So, in this case I have x 2 and S 2 as basis. and x1 and s1 as non-basic variables. So, for basic variables x2 and s2, the relative profit coefficients are 0. So, we now have to find out the relative profit coefficients for non-basic variables x1 and s1. So, let us first find out for x1. So, that is column 1. So, j equal to 1. So, Cj bar equal to Cj minus sigma Cbi Aij. So, let us look at for column 1. So, Cj bar will be computed as 6, that is the Cj for x1, and then you have to take the product Cbi Aij. So, basis is x2 and for x2 cost coefficient is 8 and Aij for x2 is half. So, 8 into half plus you have the other basis S2 whose cost coefficient is 0 and Aij is half. So, 0 into half, which is basically 4. So, basically 6 minus 4 is equal to 2. So, 2. Similarly, you can also calculate for the other non-basic variable S1 and you will find it the value as minus 4 by 5. How do you get it? For this S1 Cj equal to 0 minus sum of those two terms 8 into 1 by 10 plus zero into minus 1 by 10. So, if you simplify it will be minus 4 by 5. So, the relative profit coefficients are obtained as 2 minus 4 by 5. So, most positive is 2. So, that corresponds to non-basic variable x1. So, x1 will enter basis. So, once we determine x1 enters basis, let us find out bi bar divided by AIS bar. So, 6 divided by half is 12 and 4 divided by half is 8. So, minimum ratio rule now says that S2 will leave the basis. So, x1 enters, S2 leaves. And this is the pivot variable and this row is the pivot row. So, again we have to do elementary operations such that this coefficient becomes 1 and here it becomes 0. So, this is can be obtained by performing elementary row operations on pivot row 2. So, the pivot row is row number 2. So, to convert this half to 1, we multiply second row by 2, so that half becomes 1, and then to make this 0 in the first row, we perform first row plus second row into minus 1. So, now we get tableau 3. In the tableau 3, we have x1 and x2 as basic variables and S1 and S2 as non-basic variables. So, for basic variables, we can straight away write the relative profit coefficients as 0 and we have to find out the relative profit coefficients for the non-basic variables S1 and S2. We find that for S1, which is column 3, j equal to 3, you find the relative profit coefficients as Cj bar equal to Cj minus sigma Cbi Ai j. So, Cj bar equal to Cj minus sigma Cbi Aij. So, following these expressions you can find for S1 as well as S2 and you get the values as minus 2 by 5 and minus 4. So, now you note the values for the Cj bar. For the basic variables, these are zeros. For the non-basic variables S1 and S2, I have minus 2 by 5 and minus 4. So, all the relative profit coefficient Cj bar is less or equal to 0. So, that is the condition of optimality. We have reached optimality conditions. So, what is the value of the Z at optimality? X1 equal to 8, X2 equal to 2 is the solution. So, Z equal to 6 x 1, so 6 into 8 plus 8 x 2, 8 into 2, so 48 plus 16 is equal to 64. So, now there is no need to compute the minimum ratio because we have already reached optimality. So, the optimal solution is x 1 equal to 8, x 2 equal to 2 and z equal to 64. So, this is the summary of all three tableaux that we have performed. So, this was the initial tableau, tableau number 1, where S 1 and S 2 was basis and x 1 and x 2 was non-basic variable. In the next, we got x 2 as basic variables and S 1 became non-basic variable, and finally, we got both x 1 and x 2 as basic variables and S 1 and S 2 as non-basic variable. So, the final solution is x 1 is equal to 8, x 2 is equal to 2 and z is equal to 64. So, this is how you can do the computations for solving linear programming problem using simplex method. This will require some practice and you have to take care that you do the multiplication and additions or elementary row operations correctly. So, there are three main things. You must perform the elementary row operations correctly, and then you must compute the relative profit coefficients correctly, the most positive coefficients corresponding to that non-basic variables enters as basic variable, and then compute the minimum ratio rule. From the minimum ratio rule, you will be able to determine which basic variable leaves. You go on doing these computations in tableaus as shown until you get all Cj bar less or equal to 0. That is the condition of optimality. With this, we will stop here.